Good afternoon, everyone. My name is Lindsay Ulizio, and I'm here with my colleague today, Sam Boso. We work for Whitman Requart & Associates, and we're here today to discuss with you on how to tackle typical and atypical traffic conditions with both traditional and TSMO solutions. We're going to be using both PTV Visum and VSIM. We'd also like to give a special thanks to our collaborative partner and client, M.SHA, for this particular transportation systems management and operations project. So this project study area, it includes 3 main routes within Baltimore and Maryland counties, Maryland. The primary focus is I-70 from Maryland 32 on the western side all the way to the I-695 interchange. The other 2 secondary routes, one is US 40, which runs parallel to I-70, as well as US 29, which runs perpendicular. The purpose of this study was to identify both existing and future needs, and then to come up with established goals based off of those needs, and then to develop concepts with both traditional and TSMO solutions that would improve the overall system performance. So just to give you a picture, if you're not from the area, motorists on I-70 currently experience heavy to severe congestion based off of FHWA's travel time index. There are also quite frequently extensive queues and speeds that consistently drop well below the posted speed limit. I-70 also experiences both recurring and non-recurring congestion. As you can see in this travel time index graphic, this is the AM peak. It is quite directional, the traffic congestion. Here you can see the heavy to severe congestion, the red and the dark red, is traveling along I-70 eastbound in the morning, particularly between US 40 and the US 29 interchanges. The reciprocal occurs in the PM peak direction, where you have I-70 westbound is the peak direction, with the major bottleneck being at the US 29 interchange. FHWA defines recurring and non-recurring congestion, where recurring is the typical or the expected congestion on the roadway, whereas non-recurring congestion is atypical, worse travel conditions that could be caused by incident, weather, or higher demand days. As you can see here, this was our overall analysis and modeling flow that we did for this project. We're each going to go through the components in more detail, but here is just a high-level approach right now. We started off with big data, we compiled and summarized it, and then boiled it down so that we were able to put our inputs into our PTV VSIM microsimulation model. We used dynamic traffic assignment for our models. Here we were then able to establish and calibrate our existing conditions models, which were then used as baseline models for our future no-build alternatives analysis, as well as our incident analysis. So to get into the big data evaluation, the one big component we used was the RIDIS traffic operations data, which is the vehicle probe data and incident data within the single platform. We use this data as part of our cluster analysis, which, as we've talked about after today, we're all going to be cluster analysis experts based off of yesterday and today's presentations. So we used FHWA's updated guidance to do our cluster analysis, and with that, we had our statistically based cluster bins, and we used the top right corner graphic. You see 4 different segment points within the system. So we wanted to evaluate the operations at those key locations as the system as a whole, to then boil down to get our most typical cluster that happens most frequently. And from there, we were able to determine our single representative day for the AM and PM peak periods to model and calibrate and move forward with. The bottom right graphic, just so you know, these are the 4 different routes that we had chosen because there were different route choices within the system. These were the 4 different routes that then the reciprocal was in the PM peak, in which we calibrated each route individually, as well as bottlenecks along those routes according to the guidance. The other big data component that we used was the street light origin destination data. This was essentially used as a seed trip table for the development of our existing traffic volumes in our Visum model. So we did develop a project-specific Visum model. We had started off with our VSIM model that was developed, and we brought in the network into Visum for our starting point. This did save time and was ease and smooth transition. There were, however, some manual adjustments that were required after the import, such as speeds, capacities, connectors, etc. As I said, the streetlight data was used as a seed trip table, in which we then used T-Flow Fuzzy, which is an ODME process within Visum, so that we could estimate the representative peak hour traffic volumes throughout the study area to then go into our VSIM model. So our client provided us a couple VSIM models to start off with that we were able to stitch together. And with that, that was very helpful and also a smooth transition. But there were some updated requirements that we needed to do, such as lane geometry for existing conditions. We were in 2019, signal timings, as well as we're doing the dynamic traffic assignment. So we needed to include those components as part of the model. So we used DTA rather than static routing. It was key to testing operations alternatives and the transfer of the origin destination trip tables from the Visum model. So as I said, we used these baseline models in VSIM to then create our future condition models. So as you can see here, you should all be familiar with this type of graphic by now. This is the travel time graphic as previously discussed with a 15-minute interval for FHWA's criteria for calibration. The 4 different criteria, and also we looked at the 4 different routes per peak period at the 15-minute level to be within the bounds to hit all 4 criteria, as well as bottleneck locations that were identified and refined based off of the speed data. So with that, I will pass it off to Sam to continue on with our future.
So now that the typical day and recurring congestion had been identified, established, and modeled in VSIM, we needed to find the same thing for the non-recurring congestion day. It was important for the client to identify both. So in order to do that, we took the cluster analysis that was done on the entire system and we simplified it to just include I-70 in both the peak directions for AM and PM peak hours. And when we did so, we determined that the typical cluster for that of I-70 alone matched that of the system as a whole. A little bit more of a detailed look at the cluster results is shown on the pie charts on the left. What these are showing are 4 different speed bins or clusters of speed data along I-70, going in order from slowest to fastest, cluster 1 being the slowest, cluster 4 being the fastest. The typical cluster for both AM and PM was found to be cluster 3, which is significantly slower than the fastest cluster and represents recurring congestion. Cluster 1 and 2 represent non-recurring congestion. They are significantly slower than the recurring congestion cluster. Now for us, on I-70, the pie charts on the right were the causes of non-recurring congestion. This comes from RIDIS data, where you can see weather and high demand account for most of the causes for non-recurring congestion. High demand and incidence. Weather takes a small role in it. But once this was established, we could then identify a single non-recurring congestion day that we could model in VSIM, and we could similar to the recurring congestion day, and that all of the speeds for that day would have fallen within cluster 1 and 2. So now that we had base year models for both recurring congestion and non-recurring congestion in VSIM, we were able to grow those to 2025 and 2045 using growth rates from the BMC regional traffic travel demand model. We forecast these trip tables in Visum, and then they imported them back into VSIM, where we continue to run dynamic traffic assignment to represent the path diversions that take place. And this was in the no-build models. The no-build models included all background improvements planned in 2025 and 2045, and we use the no-build models to determine quantitative goals and objectives for the alternatives to hit in order to be successful. These were based on VSIM results like based on speeds and travel times that we converted into a travel time index target that we had to hit and network delay. The generic goals of the project were just to improve conditions during recurring congestion, non-recurring congestion, and safety. Some of the alternatives we modeled, we tested both TSMO solutions and traditional solutions. By TSMO solutions, we just mean any improvement that improves the performance of the roadway without adding permanent additional capacity. Examples of that are part-time shoulder use. That's a big one that we tested, along with adaptive signal timing and ramp metering. Traditional ones we tested included roadway widening, auxiliary lanes, and modified interchanges. Examples of both are shown on the right. Top is just some typical sections that include part-time shoulder use, and the bottom is a new interchange design for US 29. We used the VSIM scenario manager for this. It was actually essential for us. We developed and maintained over 40 scenarios that were in AM and PM. I know we had the talk yesterday about not over-evaluating scenarios, but I want to be clear, these aren't 40 full-blown alternatives. These are pretty much just tweaks testing which improvement works well with each other. And this is also including AM and PM and 25 and 45. But the scenario manager, we have a picture of this shown on the right. Basically, what we would do is we'd code each improvement as an independent modification, and then we could mix and match those in the scenarios to determine which improvements paired well with others and which didn't. While we were doing this, we were coordinating extensively with the client to screen these solutions to come up with a few final alternatives that we use to pull our final MOEs for. So what are these path choices we keep talking about? I know Lindsay touched on it. This is sort of what we are sort of fighting with in VSIM and what we want to sort of represent. The AM peak, you can see the primary travel flow is I-70 eastbound toward I-695 and Baltimore City, with US 40 and US 29 being the primary diversions. The PM, the inverse is true. Some of the operational performance metrics we pulled out of VSIM, we pulled out network delay, throughputs, speeds and travel times, which we converted to end-to-end speeds, and density of level of service. We utilized the list-based results as well as the graphical results. Now, the next piece I want to talk about a little more is the incidents. We are currently still evaluating incidents in VSIM. Now, why do we need to do this? If you look at the pie charts on the right now, you can see the incidents account for over a third of all non-recurring congestion. And the pie charts on the left show non-recurring congestion is very common along I-70. So when we do model the incidents, we're going to model incident countermeasures to determine specific benefits that the roadway will see during incidents. So by the time it's all said and done, we will have quantifiable benefits shown on recurring congestion days, high demand days, and incident days. And because we did the cluster analysis, we know exactly how often each of these conditions occur. So we can tell you exactly on what days you're going to get this benefit versus this benefit versus this benefit. That was really helpful for the client. We're going to model a couple different types of incidents. The first in the AM peak was a 3-vehicle collision that closed 2 out of 3 travel lanes and a shoulder. It lasted around 15 minutes. And the second is in the PM peak, just closed 1 travel lane for a portion of the incident and a shoulder lane for the entirety of the incident. And this one lasted around 20 minutes. So how are we going to do this? How are we going to model incidents in VSIM? Well, we're going to continue to use dynamic traffic assignment to represent realistic travel diversions during incidents. Now, when you do DTA for incidents, you can't let it reach equilibrium. You have to just run it a few times to represent realistic real-time path diversions. And the next parts of incident modeling, you can do this a couple different ways. We chose to use PT routes and stops in conjunction with the COM interface and event-based scripting. PT routes and stops, we essentially would have a PT route stopping where the incident occurred that blocks a lane and forces vehicles to go around it. This is representing a lane closure. And the COM interface, we were able to use event-based scripting shown on the right, where we would employ this script that would change a driving behavior during the incident to reflect reduced capacity. So the driving behavior would be more conservative and it would serve as a capacity reduction factor. And this would be active only during the script, only during the incident. After the incident is over, the driving behavior reverts back to its original form. And after this is done, the incident countermeasures we're testing are advanced warning, where motorists will get notice ahead of time that an incident is farther down the road, and they can take alternative routes that like US 40 and US 29. That is paired in conjunction with adaptive signal timings that will be on US 40 to better handle incident flow. Now, throughout this project, we have a couple things that worked out really well for us in VSIM, and just a couple things that were a little bit harder for us. The VSIM scenario, I just want to touch on that. The VSIM scenario manager was amazing, along with the COM interface and scripting. VSIM scenario manager made it possible to test all of our little tweaks and our little pairings. We would not have been able to test a third or fourth of all of our different scenarios we tested without it. And the COM interface and scripting has been really cool for incidents. We're able to kind of see using it with the driving behaviors changing in real time and with everything happening in real time, whether it's working the way it should be or not. It's not just set behind a screen. It's easy to kind of visualize. And then we just struggled a little bit with the import between VSIM and VSIM with not everything coming in the way it's supposed to, but nothing too major. All right, that's the end of our presentation. Save questions for the end.